All right, so I'm going to go over this page here because I've been getting most of the questions I've been getting are from this page, and it's a little different because we're comparing two different scenarios. So our totals for the probabilities may be or will be different, right? So again, knowing a standard deck of cards is important. So if you're not, even just looking it up so you can actually see like the colors. Like I know you have this page, but it's in black and white, right? Obviously. So even just looking up a picture of this online, if you're not familiar with the standard deck of cards, right, it would be probably more helpful because you can actually see the colors and again, kind of, right, this was a way that I suggested that you could write on your study sheets so that you have a way to refer back to the organization of a deck of cards. So making sure that finding a way to kind of organize this information on your study sheet without taking up too much space would be helpful. Right, but anyway, so drawing a red 7, right? So there's two red 7s, right? So there's two suits that are red, and there's one number for each suit. So there's two 7s. So probability of 7 equals, so there's two 7s, two red 7s, and then, right, there's 52 decks in a standard deck. So that would be the probability of drawing a red 7, and then the probability of drawing a jack, right? So there's 4 jacks because there's four suits. So it would be 4 over 52. In this case, you may know at this point which one's already more likely to happen, right? So we're looking for which one has the greater probability, right? Probability of 7 or probability of a jack? Probability of a jack, right? Because 4 over 52 is greater than 2 over 52, right? So the answer would be drawing a jack is more likely. For this one here, we're looking at either drawing a face card or rolling a 5. So we're having kind of two different scenarios. So for a face card, right, so the probability of a face card, there's 12 face cards in a deck of cards, right? So our numerator would be 12 and our denominator would be 52 because there's 52 total. And then the probability of rolling a 5, right? There's 6 sides to a dice. So then we would have, so maybe I'll write that if you just didn't know, there's 6 sides to a die. So then the probability of rolling a 5, well, one of them, only one's a 5. So then it would be 1 over 6. Right, and in this case, it's a little more, since they're not the same number in the bottom, the denominator is not the same, it's a little hard to compare the fractions. So what I would do, right, is convert them to a decimal. So just plug in 12 divided by 52, right, that gives us 0.2308, and 1 over 6 gives us 0.1667. Right, so that would be, so now we can see it's more clear which one's greater, right? This one has the higher probability. So drawing a face card is more likely. Any questions on these so far? right? So we can look at two different scenarios, right? But in that case, we're most likely going to have a different total. So then it's easier to convert to decimal. Right, so most questions I got were stemming from just not being familiar with the standard deck of cards. So again, that's why, right, familiarizing yourself with just how a deck of cards is organized is important. So probability of drawing a club face. Right, so for this, there's 12 face cards, but only 3 of them are clubs, right? There's a jack, a queen, and a king for each suit, right? So they would be 3 over 52. And now we're comparing this to this spinner over here. The probability, we want to find the probability of the spinner landing on yellow. Bless you. Right, so the probability of yellow, how many spaces of yellow are there? Right, there's only one possible outcome of yellow, and there's 8 total spaces that we can land on. So the probability of a yellow would just be 1 over 8. Right, and again, this is a scenario where we have fractions aren't easy to compare. So I convert it to a decimal, right? So this would be 0.05 to 77, and this would be 0, right? 1 over 8 would be 0.125, right? So it so happens that, right, rolling that or spinning a yellow space on the spinner is more likely. Right, so again, for this one, we have rolling a multiple of 3. So again, we have a dice. Probability of a multiple of 3. So what is this? What is a multiple of 3? Exactly, yeah, so those are all multiples of 3. So a multiple just means, right, if we multiply 3 by any number, that gives us a multiple of 3, right? So 3 is a multiple of itself, because we can just multiply 3 by 1. 6 is a multiple of 3, because we multiply 3 by 2, and so on. But we only go up to 6, so there's 2 possible ways, a 3 or a 6, right? And then there's 6 sides, right? And then this time we're using the spinner again, but we want the probability of spinning a green, right? So there's 2 possible ways to spin a green, and there's 8 possible ways to land on any of the spaces in the spinner. Right, so 2, 6, this equals 0.3333, and this equals 0.25, right? So this is more likely. And then the last one here, drawing a red card, right? The probability of drawing a red card. There's 26 red, right? The rest are black cards. So it's 26 over 52. And then the probability of, right, you spin a red on the spinner. There's three ways that we can spin a red card, a red space, and there's 8 possible spaces. Right, so this, if we plug it in to our calculator, is actually 0.5, right? And we know that this is less than 0.5, but if you didn't see that, do 3 divided by 8, right? That gives us 0.375. So this is more likely, right? So drawing a red card is more likely. Right, so again, nothing necessarily new here. It's just we're comparing probabilities now. So when we ask what's more likely to happen, you just have to find the probabilities, and then the one that has the greater probability is more likely. Any questions on this page before we move on? So I want to cover, sorry, I guess, is there any questions? All right. So I'll leave page 25 for you to do. And I can post the solutions to these. So again, it's just looking at what's more likely to happen. Right now, for example, this one, we can start including the odds, right? So then you'd have to convert odds to probability in order to find what's more likely to happen. So we're going to go to page 27. So I want to kind of cover this because tomorrow I'm thinking we may do, right? So obviously game, is anyone familiar with the game show Deal or No Deal? No? Really?
You just watch Netflix these days.
Yeah. Okay, well, that doesn't really matter. Well, we'll see. I was thinking of like simulating a deal or no deal game and finding probabilities with that. So, but this, I want to cover this so that I can include this in tomorrow's lesson. So far, we have been dealing with, so there's two different probabilities, right? So there's theoretical and experimental probabilities, right? So they sound complicated, but right, every probability that we've been dealing with so far has been a theoretical probability. It's what we are predicting is going to happen, right? So the probability of an event A occurring based on possible outcomes. So theoretical probability is the probability of event A occurring based on possible outcomes, right? So the key here is possible outcomes, right? So maybe I'll rewrite this here, right? A theoretical probability, which is what we've been dealing with, doesn't actually tell us, it's a prediction, right? It's not what actually happened. So probability, or I'll say theoretical, I'll use TP here, and EP. So for TP, theoretical probability does not tell us what actually, right? What actually, it doesn't tell us what actually is going to happen. We don't know right? So when we think of expressing probability in words, right? Rolling a dice. I'll keep going back to rolling a dice because it's, right? So a dice has 6 sides. Probability of rolling any number, so let's say 6, is 1 over 6, right? But we think of that as 1 out of 6. So what we expect, what does that tell us? We expect that 1 out of 6 rolls will be a 6, right? But if we actually roll a dice 6 times, we may not roll a 6. right? So that would be our experimental probability, right? So it's what actually happens. So again, total theoretical probability does not tell us what actually is going to happen. It is just a prediction. Right, so we have this formula, and it's what we've seen. It's the formula we've been using to find our fractions for our probabilities. So we're used to see every probability we've been dealing with so far has been theoretical. Experimental probability is what actually happened, right? So if we actually roll a dice 6 times, what actually happens? So the probability of event A occurring based on trials, right? Based on trials, experiments, or surveys. Right, so if we actually roll a dice 6 times and we don't roll a 6, then what would our probability be based on that experiment of rolling a 6? If we rolled it 0 times out of 6 rolls, 0. It would be 0 based on that experiment. Experiment only, right? So it's a similar. So really, it's really just the wording that changes. The formula is right. Still gives us a fraction, right? It's just based on a number of trials. So for the rolling dice example, it's just the number of times we roll a dice. So in general, when we perform experiments involving events where there is no bias, so that means experiments that, right, no bias can also mean, right, fair. The experimental probability should be similar or equal. So the experimental probability should be similar or equal to the theoretical probability. Because again, the theoretical probability is a prediction, right? So they should be close together. The main reason they may be different is because of a small sample space. Main reason they may be different is because of a small sample space. So that's important because we're going to look at how the number of trials we do affects probability. Right, so let me ask you, if we roll a dice 6 times, right, it's more likely that we won't roll a 6 than if we roll a dice 1,000 times, right, there's a good chance we're going to roll a 6, right? But if we roll a dice just once, right, well, there's a pretty good chance that we won't roll a 6, right? So that's why sample space is important when calculating experimental probability. So this little table here, right, is saying that we have a small sample space, right? A small sample space leads to our experimental and our theoretical probability not being close, right? So small sample space, I'll say EP is not close to theoretical probability, right? But if we have a large sample space, we expect our experimental probability will be close or equal to the theoretical probability. Right, so this note here is important, and it's when we make a prediction and you know both probabilities, right? So if we want to make a prediction, we always use the theoretical probability, which is what we've been doing right so far. we've only been dealing with theoretical probabilities. Excuse me. So when we make a prediction, right, and we do know both, we want to use the theoretical probability. So let's do some examples here. Right, and then I'll give you a chance to try these out on your own as well. So a bag contains various letter tiles as seen below. Right, so we have this bag here, and Alex wants to draw a tile. They record the result, then places the tile back in the bag, and this process is repeated 8 times. So, right, there's a lot of words to decipher here. So I'm picking up a tile, recording it, and putting it down, and then picking up another tile. Right, so and then this is their results. Right, so the first tile they picked was an A, the second was a B, third was an E, a G, and they picked an A again, right? So we want to state the experimental probability of drawing the letter A. So if we're looking at the experimental probability, what do we want to look at? Do we want to look at what's actually in the bag? Or do we want to look at what Alex drew in her experiment? We want to look at her results, right? Because this was, right, we can call these trial results, right? So we can say Alex performed a trial or an experiment. Right, so we want to look at these. So what is the experimental probability of drawing the letter A? Well, the experimental probability, right, so I'm going to do EP so that we can differentiate between experimental and theoretical, is of drawing a letter A would be, well, she drew 1, 2, 3, right? So they drew an A 3 times out of how many Oh, 8 times, right? Or we can just count, right? So she did this 8 times. So the experimental probability would be 3 out of 8. The theoretical probability of drawing an A, right? So this is actually what's in the bag, right? So now we want to actually see. We want to actually use the tiles that are in the bag, not the results that she got from her experiment, right? So the total number of tiles in the bag is 3, and right, how many tiles are in the bag? Does it tell us? No, we got to count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so there's 10 tiles total. Right, 10 tiles in. There's 10 tiles in the bag. Right, so we see that our total, or what we know as our total, is different because this is the total number of trials she did, or the total number of times she picked a tile from the bag. And for the theoretical probability, our denominator are the total number of possible tiles that they could have picked. So why is the experimental probability different than the theoretical probability? Right, explain. So again, theoretical probability is, right, it's just a prediction of what we expect to happen. And we can say, so since Alex, right, only drew, let's say, since she only drew a tile 8 times, right, so that's not a lot of time. She didn't even draw as many times as there are tiles in the bag. So we can say small sample size, right, theoretical probability is, let's say, different, because that's what the question says, is different from experimental probability. Right, so there's 20 minutes left. I'll give you a couple minutes. Try these out, the rest of this question, and then there are some more questions on the back. So I'll give you a couple minutes to go through these, and then I'll just write the answers out quickly right now, and I'll post them up so you can check your answers on the projector. And then you can work on some of the practice problems of calculating theoretical and experimental probabilities. Right, and I'll post these solutions as you work through them.